Welcome to this lecture. In this lecture, we are going to discuss eigenvalues, eigenvectors in a more general way. And at the end of this lecture, we will see the geometrical description of how a linear operator T acts on an eigenvector. Okay. In the end of the previous lecture, we have considered a matrix A that was 1, 4, 1 and 1. And for this matrix A, we have two eigenvalues. One is lambda 1, that is 3, and another was lambda 2, which is minus 1. Now, corresponding to lambda 1 equals to 3, we have a eigenvector that is 1, 2, and corresponding to the another eigenvalue minus 1, we have the eigenvector 1 minus 2, right? And we have the multiple t here, but we are choosing the particular one. Okay. Now, if we construct a matrix Q that is having the eigenvectors of A corresponding to its eigenvalues, तो suppose हमने ऐसे eigenvectors ले लिए हैं 1 and minus 2 like this. ठीक है, हमने क्या कंस्ट्रक्शन किया है? We have a matrix, we found its eigenvalues and corresponding eigenvectors. Then using these eigenvectors, we are constructing a matrix Q containing the eigenvector as its column. Okay. Then in that scenario, Q inverse A Q, that is similar to a matrix D where D is a diagonal matrix. D is a diagonal matrix. तो अब अगर ऐसा सिनेरियो हमने सिमिलैरिटी की डेफिनेशन क्या पढ़ी थी that A and B are similar if there exists a matrix invertible matrix P such that we can write this like this. Okay, तो यहाँ पर हमने A और B को सिमिलर मैट्रिक्स कहा था और किसी भी मैट्रिक्स A को डायगोनलाइजेबल बोलने का मीनिंग है कि दैट मैट्रिक्स सिमिलर टू सम डायगोनल मैट्रिक्स. Now, by looking at the definition of diagonalizability, you can see this Q inverse AQ. In this scenario, this A is diagonalizable matrix. Okay. So, क्योंकि ये एक diagonal matrix के similar है, that's why we are calling it as a diagonal matrix. Okay. तो हम इस तरीके से हमेशा एक प्रोसेस को फॉलो करके एक मैट्रिक्स डायगोनलाइजेबल है ये आइडेंटिफाई कर सकते हैं और इसके लिए कौन सी वो मैट्रिक्स है इन्वर्टिबल मैट्रिक्स जो कि इस तरीके से इसको एक डायगोनल मैट्रिक्स के सिमिलर दिखाती है वो भी हम आइडेंटिफाई कर सकते हैं. अगर हम आगे और फर्दर इसके डिस्कशन की बात कर रहे हैं तो ये जो डी मैट्रिक्स है विच इज़ अ डायगोनल मैट्रिक्स ये हमेशा कैसे दिखेगी क्योंकि ये डायगोनल मैट्रिक्स है तो ये हमेशा इसकी नॉन डायगोनल एंट्रीज हमेशा जीरो होगी और इसकी डायगोनल जो एंट्रीज होंगी दैट विल बी 1 एंड -3. अब 1 और 3 और -1 क्या है? दैट आर द आइगन वैल्यूज ऑफ ए. ठीक है, तो ए इस तरीके से डायगोनल मैट्रिक्स होगी और वो डायगोनल मैट्रिक्स की डायगोनल एंट्रीज ए की आइगन वैल्यूज ही होंगी. सो दिस इज अ वेरी इंपॉर्टेंट कंक्लूजन. If we want to make an general statement, then we can say if Q is the n cross n matrix, n cross n matrix whose columns are the eigenvectors in beta. Okay, in beta, then the matrix Q inverse A Q is a diagonal matrix whose diagonal entries are the eigenvalues. Okay. Now for the next discussion, we know that whenever we have a vector space V over the field F, then if we choose the n copies of this field, that means Fn, okay, then we can always establish a function phi from V to Fn, and this phi is a isomorphism, okay, and every ordered basis of this vector space V will decide an isomorphism, ठीक है, और ये प्रोसेस हमें एक ब्रिज कंस्ट्रक्ट करके देता है टी और इसके मैट्रिक्स रिप्रेजेंटेशन में, ठीक है। अब ये किस तरीके से प्रोसेस है उसके बारे में हम बात करते हैं। लेट वी बी अ फाइनाइट डायमेंशनल वेक्टर स्पेस ओवर एफ, ठीक है, एंड लेट बीटा बी एन ordered basis for V. Then the function, then the mapping phi from V to Fn defined is the phi image of V. Phi of V is going to be the coordinate vector of V related to the basis beta, ठीक है, and for this B we are using this phi B, okay. So for every ordered basis beta we can always define this kind of a mapping from V to its n copies of field. Then we have two most consequences for this phi, that phi B is a linear transformation from V to Fn, and the another is this phi B is an isomorphism किसी भी दो स्ट्रक्चर के बीच में आइसोमॉर्फिज्म का डिफाइन होना एक आइडियल सिचुएशन है, क्योंकि उस केस में हमें किसी एक की ही स्टडी करनी है। तो हर एक वी के लिए हम हमेशा फाइनाइट डायमेंशनल होना चाहिए। तो इस तरीके से हमेशा हम एक ऑर्डर बेसिस के थ्रू एक फाई बी को डिसाइड कर सकते हैं, एंड दैट फाई बी इज अ लीनियर ट्रांसफॉर्मेशन एंड ऑल्सो एन आइसोमॉर्फिज्म, ओके। Now, based on this discussion, we are going to relate this T and its matrix representation in the context of eigenvectors. Okay, so let us start that discussion, which says that let V be a finite dimensional, you can consider it as a lemma, okay. V be a finite dimensional vector space over the field F, ठीक है, and let T be a linear operator on V, and beta be an ordered basis for V. Consider, this is very important statement, A is the matrix of T related to the basis beta. Then in that scenario, then V belongs to, then you can say, then this V belongs to V n eigenvector of t corresponding to eigenvalue lambda if and only if phi beta of v is an eigenvector of a. Okay, eigenvector of a corresponding to eigenvalue lambda. Okay, so let us understand this statement in more clear way. Suppose we have T, then we can talk about its matrix representation under this beta. Suppose we are calling this matrix A, and suppose we have eigenvalue lambda, and corresponding to this eigenvalue lambda, we have eigenvector V. Now, if we decide this V from the vector space V, capital V, then we can always talk about its phi b beta image, then this phi beta image, that is phi beta of V. That will be eigenvector of this matrix corresponding to the same eigenvalue lambda. So this is the circle we have, and you can say this is a pass bridge between this linear operator T and this matrix T beta. Okay, and the proof is very much simple. It is containing only the definition of being an eigenvector. So for the proof, suppose that V is an eigenvector of T corresponding to the eigenvalue lambda. Then we have T of V must be equal to lambda V. This is the definition of eigenvector corresponding to the eigenvalue lambda. Then अब हमें this phi beta of V is an eigenvector of A, तो हमें क्या कैलकुलेट करना है? You want to find this A image of phi beta of V, and we will identify that this must be equal to, you can say this must be equal to some lambda time phi b of V. अगर हम ऐसा बाई सम कैलकुलेशन अगर ऐसा हम कर पा रहे हैं, दैट मीन्स दिस phi beta of V will be an eigenvector of this A corresponding to the eigenvalue lambda. Now by the definition we can write this A of phi beta of V, that is the left multiplication transformation, that is LA, that is same as LA of phi beta of V, right? And now this LA phi B, you know very well that this is the same as the phi B image of T of V. Okay, the LA phi beta is same as phi beta of T. Now phi beta T of V, that is same as phi beta, this TV is nothing but lambda V, and this phi B is homomorphism and linear operator, linear transformation. Then we can write phi beta lambda V as lambda phi B beta. Now since this V is not equal to 0 and this phi beta is an isomorphism. Okay, so these two things implies that then phi beta of V has to be equal to not zero, क्योंकि आइसोमॉर्फिज्म के अंडर नॉन जीरो वेक्टर की इमेज नॉन जीरो वेक्टर ही बनेगा. Now since phi beta of v is its A image is lambda time phi beta of v, and also this phi beta v is not equal to 0, that means this phi beta v is an eigenvector of A corresponding to lambda. तो इस तरीके से हमने ये देखा कि अगर दिस v is eigenvector of t, then its phi beta v is eigenvector of A, where A is linear matrix representation of the linear transformation. Let me conclude this statement that suppose V is a finite dimensional vector space and we have a T linear transformation, okay, from V this F to suppose V to F. Now dimension of V is suppose n. Now what is phi beta? We are having an ordered basis of V, so we have a image or a function between V to Fn, okay. Fn is n copies of n, then this function is phi beta, right? Now under this phi beta we identify a mapping A from Fn to Fn, right? And this A mapping, okay, that A is the linear matrix representation of linear transformation T. तो इससे इसके अंडर इस phi beta की जो इमेज मिलेगी that will be the eigenvector of A, okay.